So let us talk about, if you have given and line which is the R, set of all real numbers, is as a line is given to you, and if I fix this point 0 here, and if I have one point here x, or I can say x is here and y is somewhere say here, then how to denote this distance between x and y? As we know, we can denote, if this internal points x and y is there, then we have x minus y. This is the way we can have to represent any point on this real line, or a distance between 2 points on the real line. Now let us discuss what are the properties of this distance between 2 points. So the first property one can observe, that the distance is always positive. Okay, that means this mode of x minus y is always positive. That is the first property of the distance, we can say. Okay. Second property, if I want to say that distance between 2 points is 0, can I say that both the points are same? So if you have 2 points on the real line, and you know that the distance between these 2 points is 0, that means that 2 points are the same. That is the second property, fundamental property that we can have. And third property that we can observe is, if you can measure the distance between x and y is the same distance between y to x. So if you have a distance between x and y is same as y to x, that is the third property that you can observe. So that is called the symmetricity of the distance. So if you measure from x point to y point, the same distance will happen from y point to x point. That is the fundamental things that we can notice for the distance. And the fourth point, or fourth fundamental things we can observe, if you have another point, let's say z, onto this real line, then we can observe that a distance between this x and z is always smaller than distance between x and y plus y and z. Whatever this x, y, z, I may say it is arbitrary points, and the same thing you can have in the, why I have written d, it is actually distance I should write. So you know that the triangle inequality for 2 numbers x and y, I can say the mode of x minus z plus z minus y. This triangle inequality you have probably also learned in the course of complex analysis in the previous semester. So that is the things that we can say, that distance between x minus y is less than or equal to distance between x minus z plus z minus y. This is a triangle inequality that we have. So this is in the case of R. We have observed this the same scenario in the R. What will happen in the R square? Suppose I have now R square, that is x, let's say this is x axis and this will be y axis, and there are 2 points given onto this R square or xy plane. Let's say this coordinate is x1 y1 and this will be x2 y2. We know that the distance between these 2 points, let's say this is the point A and this will be the point B. So I can denote that A minus B if I want to denote, as this is the notation I am writing, the distance between A and B. And we know that the distance formula in the geometry, in coordinate geometry, we have learned that that is square root of x1 minus x2 square plus y1 minus y2 square. This is the distance between two numbers that we can have. The same thing as we have observed in the previous slide or for R, can we state for here also? So can we say that the distance between any 2 points in R2 is always positive? Sorry, always non-negative. The second, if I can say the distance between 2 points is 0, can I say both will be 0? The third, the distance from A to B will be same as always distance from B to A. And the fourth one, if I have another point, let's say C, then in the triangle also we have the same concept that the one side is always smaller than sum of the other two sides. That is a triangle inequality. So I can say that the distance between AB is always less than or equal to distance between AC plus CB. That is the triangle inequality. This is the case in the R2 we can have this thing. Now we can generalize this concept for any space Rn. So that means we know the distance between 2 points into the Rn. We know the formula, that is the square root of, let's say the 2 points are in Rn, it is x1 up to xn, and D will be y1, y2 up to yn. These are the 2 points we can have. And the distance between AB, we know it is square root of x1 minus y1 square plus x2 minus y2 square up to so on xn minus yn square. And this distance between AB also satisfies this property. Okay. Now I can have one more question here. Let's say this is the y-axis and z-axis, x-axis and y-axis is there, and there are 2 points A, B into this. And there is another point C. Let's say point C is here. Instead of defining the shortest distance, that we are saying that this distance from point A to B, but I may define the distance always go through with this point, or I can say that you always first go to the origin. So please bear this. This is the straight line that I want to draw it. Okay. So let's say this is the point AB or origin, and from B to origin. So if it is O, so I am defining the distance now, or distance between AB. Okay, so I'm just denoting this notation AB. The distance from A to O that we have in the previously, which we have defined, distance A minus 0 plus B minus 0. What is modulus of A minus 0? That is origin. This is not 0, but it is origin. So that is here we have defined. So if you the question is, can we define such type of distance between A and B? What is your answer to this question? That means, can we say this is the a distance between this point AB. So it is a question, or it is the situation like, if I want, suppose there is a 2 point, or I can say I want to deliver some goods to point A to point B, then it's always you have to go to the hub and then from hub to the point B. So any salesperson, you want, suppose the Zomato person is there, he want to deliver some goods and he get the order from the customer. So let's say B is the customer. Okay. A get the order, and then what will happen? He will go first to the pickup point. That means whatever the goods you want to supply, he go to that point, and then from that point he will deliver to the person or customer. Okay, so this is the situation like this. In general, if you can have, then can we define this is as a distance? The question is. So what is your answer? And I am talking this A and B are in general any point on the R2. You can take any point on the R2 and we can be defined like this, and can we say this is the distance between. That means it should satisfy, whether it will satisfy this all 4 conditions. So if you can write down this is into the Cartesian form that we have here, what is your x2 and y2? Into this case it is 0. So it is a square root of x1 minus 0 square plus x2 minus 0 square. This is the things we have. Okay. So what is this? It is square root of x1 square plus, I will denote x1 y1. So it is y1, not x2. So it is y1 minus 0 square. So it is x1 square minus y1 square, and for this one it is x2 square plus y2 square. So it is defined like this. Distance. Can we say this is always positive? That is the first situation. Can we say this distance between AB, which we have defined like this, is always positive? Yeah, because this is positive, this is the sum of the 2 positive numbers, it's always positive. Can we say if the distance between these 2 points is 0, then you can only A is same as B. That means if this is the 0, then this will be 0. If this is 0, this is positive non-negative number, this is non-negative number, sum of 2 non-negative number is 0, then both of them are 0. So x1 is 0, x2 is same argument will given, and vice versa. So this is the situation is also there. Third point, that means the distance between AB will be same as distance between BA. Can we also say this? That means if you go from here to this point and then from this to this point, will be same as from this to this point and from that to this point. Obviously by logic it will be the same. So just without proving, I am just writing that. And the fourth, that is a triangle inequality. That means there is another point C is there here. If you go from A to B, and which is always less than or equal to A to C plus distance between C to B. That is also true, that you can check. So the question is likewise, can we define another way to a distance? Okay, so how many ways we can have? So there are, you may define lots of ways to define a distance between this any point on this AB. In general, in any space, here I have taken the example of R2. But suppose you can have the sphere, that means on earth, There are 2 points on the earth. How to define a distance between that 2 points on earth? Okay, so that is some criteria, some things which has to be defined. Or if can I say this is the distance between 2 points, in which way we can define a distance between 2 points on earth? So in general I am talking about any arbitrary set. If you have given any arbitrary set, can we able to define a distance between 2 points on that set? Okay. So here I have explained you the examples through the example on R, on R2, on R3 or an Rn on a sphere. Likewise, you can have any object. Can we define a distance on that object? And so that's why to define a distance on any object, that is the definition of a metric. So what will be the definition of a metric? So for that you require one set which has to be non-empty set. So let X be a non-empty set. The function D from X cross X to R. Why I am saying that it is a function? So distance is actually a function. It is a function. So I am saying it is a distance from point A to B. So this point A and this point B is from whatever the set you have taken. And it is a function from X cross X to R. So this is X and this is a cross sign. Satisfies the following condition. First one, it has to be for every X and Y, X, Y and Z belongs to X. First one is we have D of XY is greater than or equal to 0. So the distance between any 2 points is always non-negative. The distance from XY is equal to X is equal to Y. That means if distance is 0, then that 2 points are equal and vice versa. If their points are equal, that will be the things. The symmetricity, that is the distance from X to Y will be same as Y to X. And the fourth one is the triangle inequality, that is distance from X to Y is less than or equal to distance from X to Z plus Z to Y. Then this D, it's called a metric on X. And the order pair X comma D, it's called metric space. Okay, so this is the definition of metric and a metric space. So in general, in short, somebody asks you what is a metric. So in short, you can say that metric is a generalization of a distance on any arbitrary set X. Okay. And what is metric? It is a function from X cross X to R and which satisfy these 4 conditions. So in that way, we can have a definition of a metric or in general metric space. So to define a topological structure on any space, okay, or to define some metric on the space, it will gives you distance structure on that space, and from that distance structure we can talk lots of things. We can talk about the derivative. See, all this concept is required to define a derivative integration on, in general, any arbitrary space, because if the distance structure is not there on the space, we cannot talk about derivative, differentiation, all sort of things. So that's why these concepts are much important. Distance structure is important on any arbitrary space, and you will learn about some more things onto this in your further studies. Okay, so what are the examples of a metric? So let us talk about the first example, which we already discussed. So the question, or I can say, prove that R comma D, R is the real number, set of all real number, is a metric space where D of xy is defined as mode of x minus y for every xy belongs to R. So R is a real number, set of all real number, and this way, if we define this D, then it will become a metric space. The solution, or I can say it's easy, what we can have to check, first of all, R is a non-empty set, that we know. So we note that R is non-empty. That's required. If it is empty, then we cannot define a distance on it. Then we also note that, distance between x and y, which is mode of x minus y, and we know that the modulus is always greater than or equal to 0 for every xy belongs to R. This is, we know. So we can say the first condition is satisfied. The second one, distance between x and y will be mode of x minus y is 0, which implies, we know that the modulus is 0, that means x minus y is 0, and which will implies x is equal to y. And if x is equal to y, we will have x minus y is 0, and so the modulus will be 0. So the second condition is also satisfied. For the third one, the distance between x minus y, which is modulus of x minus y, and this we can write down minus of y minus x, and we know that mode of x is same as mode of minus x. So that's why this will be mode of y minus x, and so this is d of y x. The third condition is also satisfied, and this is true for every xy. So I should write down for any xy belongs to R. This is true. And fourth one, for any xyz belongs to R, I can say distance between x and y will be nothing but the x mode of x minus y. If I add and subtract z here, then add and subtract z, then we will have this, and that is less than or equal to mode of x minus z plus z minus y by triangle inequality, and hence distance from x and y is less than or equal to distance from xz plus zy, but this will be the same as distance from xz plus, so this is zy, this is xz. Okay, fine. So that's required. This is the things required. So hence we can say that D satisfies all four properties of metric. Therefore, D is a metric on R, and hence R comma D is a metric space. Okay. Let's have the another example. The function D from R square cross R square to R defined as D of xy is equal to mod of x1 minus x2 plus y1 minus y2 for every x is equal to x1 y1 and y will be x2 y2. Both of them belongs to R2. Then prove that the D is a metric on R square. Okay. See here, the metric D has the codomain, or codomain is R, but range will be this. Always, no? This is the always thing. The range always will be this, whatever the codomain is. It not make any difference. But the range of that function D is always this one, because the first condition says that. So instead of this R, if somebody write this one, then also it is fine, no problem with that. So here, this distance from between x and y will be this. For interested student, I may ask you, what will be the geometrical interpretation of this distance, that you can find out by your own how this distance is defined. You can stop this doing, and you can just try to find out what will be the geometrical interpretation between this distance. Can somebody have the answer for that?
Sir. Hello.
Yes.
Sir, we can say that if we imagine the plane to be a grid made out of horizontal and vertical lines, then for any point lying on a vertex, this distance is equal to the number of squares along whose boundary we will have to travel to get to that point, the shortest number of.
Yes. So first of all, yeah, you are going into the right way. See, what is this first of all, what is the meaning of this mod of x minus y? So here, see, this is the distance, I can say, if this is the point and this is the A and B, then this distance is x1, that we know. Okay, this distance. And what is x2? It is from this point to this. This is x2. Okay. So what will be this mode of x1 minus x2? The mode of x1 minus x2 is this. That is the point from this. Let's say this is the point C, or some another point, whatever. Star point. Let's say this is a star point. So this point A to star point B, this vertical line is the mode of x1 minus x2, and from B to this, or I can say, what is y1? Y1, sorry, I have done wrong thing. It is actually y1. So let me explain you again. Okay, so what is this distance from this point to this? It is actually x2. So this distance is x2. From here to here, it will be x2. What is x1? X1 distance is from this point to y-axis. So this distance now is actually mode of x1 minus x2, and this distance that we have here, in similar manner we can say it is y1 minus y2, mode of y1 minus y2. So this distance between x and y here, it is actually this. First you should go, you can calculate from this to this and then go to that way. So this is the, so in general you can just say that as somebody saying that you can consider one grid of horizontal and vertical lines. If you want to find out the distance between these 2 points, then you have the distance is this, neighboring, whoever the neighbor, either you can have this one or this one, whatever. So this is the way this distance is defined. Okay, so if you want to measure distance between these two, then this is the distance between these two, not this diagonal one. It is always go through with that point. So in that manner, this distance is defined. Now let us try to prove in general. To prove this is a distance, I need to take 3 points into the R2. So let us take x is x1 y1, y will be x2 y2, and z will be x3 y3 into R2. They all belongs to R2. Now, first things that you need to prove that the non-negativity condition, that is d of xy, as per the definition it is x1 minus x2 plus y1 minus y2 is there. Since mode of x1 minus x2 is always greater than or equal to 0, and mode of y1 minus y2 is also greater than or equal to 0 for any x1, x2, y1, y2 belongs to R. If this any real numbers, then we always have this thing. So that's why d of xy is greater than or equal to 0. The sum of two numbers is always greater than or equal to 0. That is the things we can have. The second, d of xy is 0. Then we can say that mode of x1 minus x2 plus y1 minus y2 is equal to 0. And both of them are non-negative, so that will implies mode of x1 minus x2 is 0 and mode of y1 minus y2 is 0. So that will implies x1 is equal to x2 and y1 minus or y1 is equal to y2, and vice versa. If this is the x1 is the same as x2, y1 is same as y2, we can say that this is the things. So this is if and only, this is also if and only, and this will gives you x is same as y. So that's why the second condition is satisfied. The third condition that we have, d of xy is same as d of yx. So for that I'm starting with the definition, that is mod of x1 minus x2, and as per the definition of the modulus or property of the modulus, we can say that this is x2 minus of x2 minus y1 x1, and this is minus of y2 minus y1. So this will be x2 minus y1 plus y2 minus y1, and hence this will be d of y x. So the third condition, that is the symmetricity, is true. Fourth condition, d of xy, I am starting with x1 minus x2 plus y1 minus y2. I am adding and subtracting z x3 here and y3 here. That is x1 minus x3 plus x3 minus x2 plus y1 minus y3 plus y3 minus y2. So by triangle inequality for real numbers, we can say that this is x1 minus x3 plus x3 minus x2 plus y1 minus y3 plus y3 minus y2. And if we can combine now this two modulus and this two modulus, the red one will gives you, that is equal to actually d of xz, because we have defined z as x3 y3, and this green one will gives you d of zy. So that will prove that this d satisfies all the four conditions of the metric. Hence D is a metric on R square. Can we generalize this example, and I am giving you as a homework? So instead of R square, I may define, so this is your homework that you have to do it yourself. Instead of R square, I am be defined for Rn in general. So the function from D Rn cross Rn to R is defined as d of xy, or I can say x bar y bar, is equal to summation I running from 1 to n mod of xi minus yi, which is actually same as x1 minus y1 plus x2 minus y2 up to so on xn minus yn for any x bar equal to x1, x2 up to xn, and y bar equal to y1, y2 up to yn. Both the points are in Rn. Then prove that this D is a metric on R power n. Okay, so this is the way you can have, is the similar way you can prove this homework. Okay, you can try for this example. Let's give you another example. Let us define a function d from R to R cross R to R as d of xy is equal to mod of x square minus y square. The question, Is D metric? Solution. So what is your answer? I can say metric on R. What will be your answer? Is this D metric on R? You have to check the conditions. The first condition, no problem, because it's always satisfied due to the modulus for any point x and y. This is true. The first condition. For the second condition, for any x and y, is the second condition is true? For example, what will be the 3 minus 3? If I have a 3 and minus 3, what will be the things? This is 3 square minus of minus 3 square. It gives you 9 minus 9, which is 0. But 3 is not equal to minus 3. Agree? So therefore, this D is not a metric on R. In that way, we cannot define this as a metric. Okay, because these 2 points, 3 and minus 3, are not equal, but distance is 0. So if according to the definition, if the distance between 2 points is 0, if and only if x has to be equal to y. This is the condition, second condition is there. And due to this, it is not satisfying. In general, you can take any point here. I can say x minus x if x is positive number. Okay, you can take any positive number x and you can work with this way. So this is in general not a metric. So now there also can be have the generalized form of this example. So can somebody have the idea how to go the generalized form of this example? That is, if I define D from R to R, R cross R to R as D of xy x cube minus y cube. If I define like this, instead of x square minus y square, I am just defining x cube minus y cube for any xy belongs to R. Question: is D is metric? Sorry, is D is metric on R? In general, if I am defining Dn R cross R to R as Dn of xy is equal to x power n minus y power n for every xy belongs to R, for which n, question, this is the question, for which n Dn is a metric on R. Both this question I am giving you as a homework. So this is also homework. This will be also as a homework I am giving you. So try to find out what are the answer for these questions. I'm giving you some more example as a homework. Let's say this. If x is equal to Rn, and define D from x cross x to R as D of x bar y bar equal to summation I running from 1 to n xi minus yi square whole power 1 by 2, where x bar is x1, x2 up to xn, y bar is y1, y2 up to yn. Both this belongs to x. Then prove that x comma d is a metric space. This is I am giving you as a homework also. Okay. So you can try for this examples. In fact, one can generalize this example also. Instead of defining this quantity, I can define like this: d of x bar y bar. Why this generalization is come into the picture? Because in the previously we have seen in this, see, this is power 1 and whole power 1 by 1 is there. Okay, here in this example power 2 whole power 1 by 2 is there. If you can see, this is in R2, it is actually a distance between 2 point x1 minus x2 square plus y1 minus y1 square x. So you can see that this is in the form of R2. Suppose instead of n we have R2, then it is nothing but the x1 minus y1 square plus x2 minus y2 square. So it is summation from I running from 1 to 2, the whole raised to 1 by 2 is there. So that's why this is the case for generalizing the normal distance in general into the Rn space. But further, one can generalize this for this thing, because in the previously we have seen for power 1, here we have seen for power 1. Okay, here this is the example for power 2. So one can generalize. This is for power p, that is r I running from 1 to n, xi minus yi raised to p whole raised to 1 upon p. For every x bar and y bar belongs to x is there, already there. Okay, this is I am also giving you homework. This is lots of examples I am giving you as a homework to prove by your own. To prove this statement, or to prove this x comma d is a metric space, for this d, this is in general people are using as dp. So dp is x bar y bar, where summation of this one is this. To prove this one, you require to use the Minkowski's inequality. If I don't know whether the spelling is correct or not, but it is Minkowski inequality is required to prove this statement. What is Minkowski's inequality? I may write down in the next slide. The Minkowski inequality is this: summation I running from 1 to n ai plus bi power p whole power 1 upon p is less than or equal to summation I running from 1 to ai power p whole raised to 1 upon p plus summation I running from 1 to n bi power p. This actually modulus. Here is also modulus is there. Here this is the modulus, raised to 1 upon p, and this p will be greater than or equal to 1. Here also I have in the previous P will be greater than or equal to 1. Okay, so this is the Minkowski inequality, and you have to require to use this Minkowski inequality to prove the triangle inequality for this structure. So only difficult part is to prove the triangle inequality. All other portion or other inequality is easy to prove for both of this. Only the requirement is to prove the triangle inequality where you have to use this Minkowski's inequality. Okay, so that's I'm giving you as a homework. And those who don't know what is Minkowski inequality or have you seen previously, they can search on internet what is Minkowski inequality. It is this, and it is nice to see the proof of Minkowski inequality. To prove the Minkowski inequality, you require the Young's inequality and Holder's inequality to prove the Minkowski inequality. So, what is the Holder's inequality? What is Young's inequality? You can also see that is they are the very important inequalities are there, which can be used for further study also. Okay, so to prove this Minkowski inequality, Holder's inequality is used, and to prove the Holder's inequality, Young's inequality is used. So you can just see the proof of those inequalities and go further with that. Let me go further for the same concept. Let's give you one more example. If x is equal to r square, and if I define a map x cross x to r as d of xy will be maximum of x1 minus y1, x2 minus y2. Okay, where this x is nothing but the x1, x2, and y will be y1, y2. Belongs to R square for any x is this, y is this. Then prove that this D is a metric on x, or I can say on R square. See, one can also see what is the geometrical interpretation of this distance. Okay, always that has to be picture is in front of you. What is the meaning of this distance? So as I have told you, if this is the point and this is the distance which we have, then if these are the 2 points A and B, x1, x2, y1, y2, then whatever the maximum of mode of x1 minus y1, that means whatever the maximum distance between these two, that you have to take as distance. That is this distances in R2. Okay. So to prove this one, I am starting with for any x bar, which is x1, x2, y bar will be y1, y2, and z bar will be z1, z2 into R2. I am taking these 3 points into this space. So to prove the first property, that is d of x bar or xy. If I have this is x bar, y bar, z. Okay. Then this will be maximum of mode of x1 minus y1, x2 minus y2. And since both this number mode of x1 minus y1 is greater than or equal to 0 and x2 minus y2 is greater than or equal to 0, we will have d of x bar y bar. Maximum is coming from the non-negative number, so that's why it is always a non-negative. So that is the things is to prove, or it's always true. D of x bar y bar is 0, which implies maximum of mod of x1 minus y1 and mod of x2 minus y2 is 0. So obviously, if the maximum number between two is 0 and both the number is non-negative, which implies that x1 minus y1 is 0, and or I can say mod of x1 minus y1 is 0 and x2 minus y2 is 0. What is my argument? If the maximum number between two non-negative numbers are 0, then obviously both the number has to be 0, and that will gives you x1 is equal to y1 and x2 is equal to y2. So that will imply x bar is same as y bar, and vice versa. If x bar is same as y bar, the components are equal. If the components are equal, that modulus is equal. If the both numbers are 0, their maximum is also 0. So second property is also true. For the third property, that is d of x bar y bar will be maximum of mod of x1 minus y1, x2 minus y2. This is same as maximum of y1 minus x1 due to the property of modulus. This is y2 minus x2. So that's why this is d of y bar minus or y bar x bar. The fourth property, that is d of x bar y bar will be same as maximum of mod of x1 minus y1, x2 minus y2. Here we shall prove that our objective is to prove that x bar z bar is less than or equal to x bar y bar plus y bar distance between y bar and z bar. That is our objective to prove. Okay, so I am starting with this. That is d of x bar z bar. Either you can start with the x bar y bar. No, that is just a number differences. So there is a maximum of x1 minus z1 and x2 minus z2 is there. So this is, I am adding and subtracting y1 here, in here and here, y2. Here in the first modulus we are adding and subtracting y1. It is x1 minus y1 plus y1 minus z1, x2 minus y2 plus y2 minus z2. Now what I will do, I may call this the first number, that is x1 minus y1 as a1. This I may say it is a2. This is b1 and b2. Let me write what I have denoted. So I am just saying that a1 is x1 minus y1. a2 is y1 minus z1. b1 is x2 minus y2. b2 is y2 minus z2. This is the things. So what is my claim? What I have to actually prove? My claim is now the distance or maximum of A1 plus A2, comma B1 plus B2 is less than or equal to maximum of mode of A1, comma mode of B1. So that is my claim. So this is the claim, maximum of mode of A1 plus A2, B1 plus B2. This is exactly the same thing which we have here, is less than or equal to maximum of mode of A1, mode of B1 plus maximum of mode of A2 plus mode of B2. See this A1, A2, x1, y1, x2, y2, z1, z2, all of them are real number. So this A1, A2, B1, B2, they are also real number. Since they are real numbers, without loss of generality, we may assume that any one of them is bigger than the other. So without loss of generality, assume that this mode of A1 is less than or equal to mode B1 and mode of A2 is less than or equal to mode of B2. See A1 and B1, A1 and B1 are two numbers, so any one of them is bigger than the other. So that's why I may assume this is the thing, and for the same way this is the thing. So therefore, if we have this, we can say that mode of A1 plus mode of A2 is always less than or equal to mode of B1 plus mode of B2. That is also true because both numbers are positive numbers, not negative numbers. So that's why this is true. Also, one note that mode of A1 plus A2, by triangle inequality we can say that mode of A1 plus mode of A2, and due to the previous thing we can say that this is less than or equal to mode of B1 plus mode of B2. So now let us see what is the maximum of mode of A1 B1. Due to this, the maximum of A1 and B1 will be mode of B1 and maximum of mode of A2 B2, mode of B2 will be mode of B2 due to the this. We can have that. Now I'll start with this slide. So now maximum of mode of A1 plus A2, B1 plus B2, which will be the less than or equal to. Due to this, mode of A1 plus A2 is less than or equal to mode of B1 plus mode of B2 and also have mode of B1 B2, mode of B1 plus mode of B2, sorry, mode of B1 B2, B1 plus B2 is less than or equal to, by triangle and inequality we can have this. So both this number and this number are always less than or equal to this number. So that's why their maximum is always less than or equal to this number. So I can say that this is less than or equal to mode of B1 plus mode of B2. But due to this, we can say this is equal to maximum of mode of A1 B1 plus maximum of mode of A2 B2, which our objective. What is this side? If I substitute the value, then this side is this side, as a1 is x1 minus y1, so we can say that this side is nothing but the distance between x bar and z bar, which is less than or equal to, due to this, less than or equal to maximum of mode of a1 b1. What is a1 b1? a1 is this x1 minus y1, a2 b1 is this x2 minus y2. So it is actually, what is that? That is distance between x bar and y bar, and for that it is y bar and z bar, another one. So that proves the triangle inequality for this, the metric. So therefore we can say that D is a metric on R2. And further, you can generalize this example. So can somebody tell me how we can generalize this example? So let x is equal to Rn. Define D from x cross x to R as D of x bar y bar will be maximum of mode of x1. This is the notation we have used, x1 y1 x2 minus y2 up to so on xn minus yn for x bar is x1 x2 up to xn, y bar will be y1 y2 up to yn, both belongs to Rn. Then prove that this D is a metric on Rn. This I am giving you as homework. So this is in general. We can generalize for, in this example I am giving you for 2 dimension. The same concept we can generalize for n dimension. Let's have one more example. This will be the last example that we are discussing for today. If this D is a metric, D is a metric on X, and X is a non-empty set. So I should write down first, let X be a non-empty set. And D is a metric on X. Define D1 of xy will be D of xy upon 1 plus D of xy for every x and y belongs to X. So for every x and y we'll have, this is the things. Then prove that D1 is a metric on X. So what is the meaning of this statement? Or from one matrix is already there, using that metric, you can define another metric on that. And this metric is always bounded metric because this quantity is always less than or equal to 1. Because d of xy is always less than or equal to 1 plus d of xy. D of xy is always greater than or equal to 0. So, this quantity is always less than or equal to 1. So it means that if you have one metric on a space X, then you can define one metric on which your X is a bounded set. Okay, so that is also one of the important things which we have to note here. So let us try to discuss the proof for this. So I am starting with for any x, y and z belongs to X. For the first property, that is d of xy, we know this. Why? Because d is a metric. So d of xy is greater than or equal to 0, which implies that 1 plus d of xy is greater than or equal to 1, which is greater than or equal to 0. So therefore, d of xy upon 1 plus d of xy is greater than or equal to 0. And so d1 of xy is greater than or equal to 0 for any xy belongs to A. So the first property is true. For the second one, that is d1 of xy, I'll start with, which is equal to 0, which implies that d of xy upon 1 plus d of xy is greater than equal to 0, and which says that d of xy is equal to 0. So which implies that x is equal to y, because d is a metric. Similarly, so conversely also we have the same thing. The third condition, that is d of xy, d1 of xy is same as d1 of yx. But d1 of xy is same as d of xy upon 1 plus d of xy. And since d is a metric, we can say that this is d of yx. Again, same argument, because d is a metric. And so this is equal to d1 of yx. So third property is also satisfied. For the fourth property, we have to prove, we shall prove that d of xz is less than or equal to d of xy plus d of yz for d1. For any x, y, z belongs to X, we have this. So now the question is to prove this one. We have this. We have d of xz is less than or equal to d of xy plus d of yz. Due to d is a metric, this is true. I'll take the reciprocal. 1 upon d of xz is less than or equal to 1 upon d of xy plus d of yz. I will add both sides 1 because I want to adjust that 1 plus. So I just write down this is as this one. About taking the LCM, we can have this is 1 plus.
Sir,
Yes.
greater than or equal to આવે. Greater than or equal to આવે ને?
हाँ, greater than or equal to આવશે. हाँ, greater than આવશે. Here greater than. Here is also greater than. So this will gives you 1 plus d of xy upon d of xy by taking the LCM, sorry, xy nothing, xz. So this is xz is greater than or equal to, here also we have the same thing, d of xy plus yz plus 1 upon d of xy plus d of yz. So this will be implies, what will be this implies? D of xz by taking again reciprocal, 1 plus d of xz is less than or equal to d of xy plus d of yz upon 1 plus d of xy plus d of yz. This will be less than or equal to, or before I can say it is equal to, by making a partial fraction. We can say that this is d of xy upon 1 plus d of xy plus d of yz plus d of yz upon 1 plus d of xy plus d of yz. Now what we have to prove is this quantity is less than or equal to d of xy upon 1 plus d of xy, and that is easy to see. Why? D of xy is always less than or equal to 1 plus d of xy or I can say d of, what I want to prove, sorry, it's 1 plus d of xy is, what we want to prove is this denominator. Okay, let me say this is we want that, what we want, d of xy upon 1 plus d of xy plus d of yz, that is the things we have here. I want that is less than or equal to d of xy upon 1 plus d of xy. So it is equivalent to, what will be this statement is equivalent to, or it is enough to prove, is this statement. So this will cancel out. So it is enough to prove that 1 plus d of xy plus d of yz is less than or equal to 1 upon 1 plus d of xz. This is enough to prove. If this is want to prove, then it is enough to prove that 1 plus d of xy plus d of yz is greater than or equal to 1 plus d of yz. So it is equivalent to prove that d of xy plus d of yz is greater than or equal to d of xy. But this is always true because this is a non-negative number and you are adding one non-negative number to this number. So that's why d of xy is always less than or equal to d of xz plus d of yz. Understood? So therefore we can say that d of xy is less than or equal to d of xy plus d of yz. Ouch, d of xy is less than or equal to d of xy plus, so we are adding just one number into that. And since this is the things, we have this. Similarly, the other thing that we have here, which also can be note that So similarly, what we have, d of yz is less than or equal to d of yz plus d of xy. This is the things. Since this is the things, we can take the reciprocal and all sort of things which we have did here. So first we have to add 1, which will implies 1 plus d of yz is equal to 1 plus d of yz plus d of xz. Now take the reciprocal, 1 upon 1 plus d of yz is greater than or equal to 1 upon 1 plus d of yz plus d of xz. Now multiply d of yz both sides. Since d of yz is non-negative number, inequality will not be changed. So using this thing, first one and the second one, and the star, this statement we can say star. We can say that d of xz, d1 of xz, which is d of xz upon 1 plus d of xz, is less than or equal to, due to this quantity is less than or equal to this quantity due to 1, we can say that d of xy upon 1 plus d of xy plus d of yz is plus d of yz. So this is, I can say, from 1, 2 and star we get this. So therefore we can say that d1 of xz is less than or equal to d1 of xy plus d1 of yz. And from this we can say that is d1 is a metric on x. So ultimately, what is the objective, or what we can say, if you have any metric using that, if you have any metric on x, using that you can define another metric on that space. This idea. Last example I am giving you as a homework. X is R and D defined as mod of x minus 3y. This is easier example, I can say. For all x, y belongs to R, is this D metric on R. With this example, we can stop here. Okay, if you have any